Hello, my name is Martin Pike and welcome to this lecture from the Ada University course on Programming in the Large. The subject of this lecture is Ada access types, and together we will complete a series of slides and then you will be assessed on your learning using some quiz questions. The slides will be presented in three sections. The first will describe the differences between different methods of allocating memory, followed by the second, which will introduce the specifics of Ada access types, and then we finish off with learning about how to carefully adhere to the rules for their use. A key piece of the learning jigsaw of Ada access types is understanding how access objects are allocated from memory at runtime. Ada access types have the same basic features as Java references or pointers in C or C++. They are designed to allow an object to be referenced from within a pool of memory, and those pools are free to allocate and deallocate objects using different methods. A common issue with pointers is the lack of any guarantee that what they are pointing at is still valid and indeed meaningful, and the design of Ada access types tries to deal with this deficiency. A key feature of Ada access types are they're deliberately typed to ensure they cannot inadvertently access objects from a different pool. Here we see an example on the left of an access type declaration that states it can only point at integer objects. Then follows the declaration of a stack object of the access type, explicitly initialized to an object allocated from a pool of memory using the new keyword. On the right hand side we see the same functionality implemented in C using malloc and C++ using the new operator. While access types in Ada do go some way to resolving the traditional problems of pointers, they are not without their own dangers. For all of their attempts, it is still possible for the programmer to induce memory leaks and corruption. The dynamic nature of their contents mean any defect involving them can be very difficult to analyze and debug, and can induce what would appear to be random behavior. Accessing objects via access types may decrease performance due to the two-step process and prove slightly more expensive than direct access. Certainly, using dynamic allocation is much more expensive at runtime than using stack objects due to the storage pool management and issues like fragmentation. In general, Ada does avoid using addresses, and unlike in C, arrays are not pointers and parameters are passed by reference. Some of these dangers are very serious, and you should give very careful consideration to regularly using access types and reserve them for when you absolutely need them. To fully understand the pitfalls of pointers, in general it would be useful to recap on the fundamental differences in the way memory is allocated at runtime. There are two mechanisms traditionally used, the first being the stack and the second the heap. Ada uses the stack for any object appearing in a declarative part, as seen in the top example where I and J occupy consecutive locations on the stack. The second example shows how access typed objects themselves reside on the stack, but the actual objects they provide access to reside somewhere on the heap. Please take some time to pause the lecture at this point and burn this image into your mind. I cannot overestimate how important this is to learning the subject of access types. Now that we have covered some of the fundamental design principles and their dangers, we will move on to the specifics of Ada access types. We now meet the syntax of access types and discuss their semantics. Starting out with the fundamental point that access types are distinct ADA types and therefore have names, scope, and attributes. The syntax uses the access all keyword along with the type of the objects to be accessed. In these code snippets we see that although t_access and t_access2 both access objects of type T, they themselves are two distinct types complying with the ADA typing rules. Additionally, there is a pull specific method of declaring an access type where the all keyword is omitted from the declaration. But this is an advanced subject and we will cover more about this in a future lesson. The last code snippet shows an example of this. There is always great discussions about the use of either numeric value 0 or the null literal constant when initializing pointers in C and C++. The ADA programming language has a reserved word called null that is unambiguously specified as part of the language. This allows the compiler to make certain assumptions about how it can be used, and access type objects can be given a default value of null by the compiler unless they have been explicitly initialized with their target object. The null keyword can also be used in comparisons and assignment statements, providing a clear specification of desired use. The following code shows some of the uses of null along with a red flag of the dangers in its use. The last line of the example is semantically correct, however very dangerous, as the allocated integer target object is no longer locatable, therefore can never be deallocated. This is a classic example of a memory leak. In our dealings so far, we've touched on the new reserved word and seen it used to explicitly initialize an access type object with an allocated target object. Remember back to our previous slides, the use of new allocates an object from a storage pool. The new reserved word is followed by the target type of the access type with any constraints required by that type. This is sensible as the allocation is going to actually consume memory from a storage pool and it needs to know the exact quantity at initialization. A qualifier can be used to copy any existing object of the target type, and this can be useful if there's a default object available or you wish to use an aggregate assignment for a record or an array. The language needs to provide a mechanism for developers to return allocated objects to a storage pool once they are no longer required. This is a fundamental tactic in the fight against memory leaks, and ADA uses a very clear and neat method of doing this. ADA requires the developer to fully understand when and how their objects must be deallocated. It does this by making the developer instantiate a generic library procedure for each and every type of storage pool object to be deallocated. To the developer, this may appear overkill, but actually this extra effort is useful as a reminder that access types should only be used when absolutely necessary. The generic library procedure is called Unchecked Deallocation, and it is available from the standard ADA library. The developer instantiates it with two generic parameters. The first is the target type of the access type named by the second parameter. In this example code, we see the access type named AnAccess declared with a target type of A type. This is then used to instantiate unchecked deallocation as the procedure named free. An access type object is created and explicitly initialized with an allocated target object of type A_type. The only body statement is then to call free, which will deallocate the target object, and very conveniently the compiler will set the access type object back to null. Once an access type object has been given a target object, it is possible for the developer to gain access to the target object by dereferencing the access type object. Dereferencing takes place by appending the .all reserved word to the access type object identifier. This allows access to the target object itself. It is similar to the way the asterisk prefix is used in C or C++. The .all suffix is optional under certain circumstances, namely when accessing the component of an array or a component of a record. Dereferencing deserves some careful attention, so we're now going to look at a more detailed example. The code starts off by declaring a record type R with two component fields, both of which are type integer. We then declare an access type to integers, an access type to strings, and an access type to the recently declared record type. A few access type objects are then declared and explicitly initialized to objects allocated from storage pools. We have one for integer, we have one that is initialized to a qualified string, and we have an access type object specifically for the record type R. The body statements will show the different types of accesses to the target objects, some of which use the .all suffix and some of which do not require it. We start off by allocating the value 0 to the target object of the vint access type object. Here we use the .all, and also similarly in the following line we use .all to assign the string CDE to the string target object pointed at by the vstring access type object. We then come on to a statement that shows that there is no need to use the .all suffix in circumstances that we have previously identified, which is accessing a component of an array or a record. So here we see that we can omit the .all suffix when accessing element 1 of vstring. The accesses to individual fields of the record type are also able to dispense with the .all suffix. So we here can see the last line is an example of that. The penultimate line shows that if you wish to access the entire record, then the .all suffix is required. Take some time to look through this example. It's very important that you grasp the difference between the target object, the access type object itself, and the syntax for how you use the access type object to get to the target object itself. A recursive data structure is very useful in programming, and in particular it is useful for linked lists or similar data structures. It is not possible to declare a recursive data structure in Ada without using a clever technique of embedding an access type object to an enclosing scope into the data structure. An example was shown on this slide of a classic single linked list. First, we partially declare a type called cell and an associated access type. Next, we embed an instance of the cell access type as a field in the full declaration of cell as a record. Identifying the end of a recursive data structure is then made much easier through using the null reserved word in a comparison statement. So far we have seen access types used for accessing dynamically allocated heap objects. They can also be used to access objects allocated on the stack. By default, objects cannot be referenced and can be optimized out in registers by the compiler. Ordinarily, no assumptions can be made about any objects instantiated using the stack. In fact, the compiler is given carte blanche on using registers for those objects where it sees fit. This presents a problem when trying to access those objects using access-typed objects. Aliased declares an object to be referenced through an access. When the objects are declared, they must be qualified with the alias keyword, and any access-type objects that wish to use the object must be initialized with object tick access. Our final section of the slides portion of this lecture will deal with the rules associated with accessibility. After this section, we will commence with the quiz. Particular care must be taken not to breach the accessibility level rules designed to stop accessing target objects that are somehow invalid. Consider the following situation where we have declared an access type for integers and an instance of the access type object declared as G. The procedure P declares an aliased integer V stack object and then uses G to gain access to it. Outside of the procedure, G.all is used. But is it safe to do this? Ada actually forbids this code due to a breach in the rules for accessibility levels. The lifetime of G exceeds that of the stack object V declared within the procedure P. When procedure P exits, the stack object V is no longer valid as the stack has been collapsed. Therefore, dereferencing G in an attempt to access V is invalid as the target object V is no longer in scope. An important concept to understand are nesting levels, which are layers of enclosing scope that can be used to structure program source code. Ada uses the term accessibility level to describe how many levels of enclosing scope a piece of code resides at, relative to level 0, which is the outermost enclosing scope. In this example code, we see 3 accessibility levels from 0 to level 2. The rule states that it is only possible for library level code to access level 0 objects, and for other levels to only access target objects that remain in scope for at least as long as the access object itself. Normally this means any of the enclosing scopes. This makes sense because the stack collapses at the end of each enclosed scope, so access objects in the enclosing scope will be targeting areas of the collapsed stack, which is invalid. The primary message for you to take away from these slides is try very hard to avoid nested access types. Here we see an example where at level 0 we have an access type declaration T0 for integer target objects. We create an instance of this as A0 and then an aliased integer stack object is declared. Procedure proc then declares its own access type for integer target objects. It then declares an instance of this and another aliased stack object. Remember that an access type object can access an aliased stack object by using its tick access attribute. The first error is due to A0 being declared at a higher level compared to the target object V1. Similarly, with the second error, even though it has type converted the access type, the target object is declared at a lower level than the access type object. The third error is due to the target object A1 also being at a lower level than the access type object A0. In the previous example, you may have noticed the use of a variant of the tick access attribute called Unchecked Access. It really is up to the developer to determine when and why it may be okay to use unsafe access to data. Ada provides the Unchecked Access attribute to intentionally allow a breach of the accessibility level rules and access a stack object of an incompatible accessibility level. I cannot stress enough how dangerous the use of this attribute can be, and I hope you can appreciate this message. If you encounter the use of unchecked access when reading program source code, then please be aware that it may have been used by a programmer who didn't know any better. We've now reached the end of the slides section of this lecture. You should now have enough knowledge of Ada access types to complete a small quiz with questions designed to test your understanding. Good luck. We will start off slowly and ask you to determine if the following code is correct. An access type is declared, called an_access, for the integer target type. An integer w is declared and its tick access attribute is used to explicitly initialize v, which is an object of the an_access access type. Is this code correct? Click on the tick icon if you believe the code is correct, or the location within the code you suspect is wrong. In this case, the code is incorrect. Use of the tick access attribute is restricted to stack objects that have been explicitly declared using the aliased reserved word. Here we see that w was not declared with the aliased reserved word, so cannot be accessed from any access types. Question 2 modifies the previous code slightly, and so we ask the same question of you. Click on the tick icon if you believe the code is correct, or the location within your code you suspect is wrong. Perhaps surprisingly, this code is incorrect. In order for access type objects to use stack objects as targets, the access type must be declared with the all reserved word. It is recommended that developers always use the access all method of access type declaration for increased flexibility. In this question, we continue to use the an_access access type declaration for integer target types. There is now a procedure proc with an empty body, but two stack objects in the declarative part. W is an aliased integer, and X is an instance of the access type that is explicitly initialized to use the tick access attribute of W. Click on the tick icon if you believe the code is correct, or the location within the code you suspect is wrong. Unfortunately, this code is incorrect and will fail to compile due to a breach of the accessibility level rules. X is of accessibility level 0 because of the level at which its type was declared, while W is of accessibility level 1. Allowing this declaration would permit reference to the object outside of the correct scope. Now we encounter a record type R and the declaration of an access type that uses the record R type as its target object type. The procedure proc declares an access type object and explicitly initializes it to access a dynamically allocated instance of R. Both fields within R are accessed in the body of proc, one using the .all reserved word and one that does not. Click on the check icon if you believe it is correct, or the location of any errors that you suspect. On the whole, this code is syntactically correct, as access type objects can reference components of their target object with or without the .all suffix. There is a clear memory leak with this code though, as the dynamically allocated instance of R can never be returned to the storage pool. When the procedure proc exits, the V stack object will be lost. Therefore, no other part of the source code can deallocate the object that V targeted. Question 5 declares an aliased integer stack object at level 0 called G. Procedure proc in turn at level 1 declares an access type that targets integer objects from any storage pool, including the stack. An instance of this access type is declared as the object V. The only body statement uses the tick access attribute of the level 0 stack object G as the target of V. Is this code correct? Click on the tick icon if you believe the code is correct, or the location within the code you suspect is wrong. This code is correct, as the accessibility rules allow access to stack objects declared in enclosing scopes. The access type A_access exists at level 1, but it can target objects declared at level 0, such as G, as its scope is of a lower level. Remember that under the rule, objects declared in an enclosing scope are accessible by an enclosed scope. The next question introduces a slightly more complex situation of access types using other access types as their target types. Here we have a simple record declaration for R, followed by an access type declaration with the target type being set to R. The next declaration is of an access type where the target type is the previously declared access type R_access. We then go on to create a stack object of the double targeted R access type, and the body contains various statements that access and manipulate this stack object called V. Click on the tick icon if you believe the code is correct, or the location within the code you suspect is wrong. Most of the statements are correct, except for one that will cause compilation to fail. The line v.f1 is invalid, as it is not possible for the .all to be emitted on a double targeted access type. Remember that the .all can be emitted only when accessing a component of the target object, and in this case the target object is itself an access type which doesn't have any components. Question 7 will test your knowledge about returning allocated objects to the storage pool. The code starts off by declaring an access type that targets all integer objects from any storage pool, including the stack. The generic procedure Unchecked Deallocation is then instantiated as the procedure free, with the access type and the target type being specified in the generic contract. Two stack objects of access type are declared, with the first being explicitly initialized to an allocated integer, and the second being explicitly initialized to the same target object as the first. The body includes a call to free with v1 passed as the argument, followed by a call with v2. Is this code correct? Click on the tick icon if you believe the code is correct, or the location within the code you suspect is wrong. The code will compile, however, at runtime, the second call to free should raise a storage error exception. v1 and v2 both point to the same target object, so when the first free completes, the target object has already been returned to the storage pool, yet v2 still contains a reference to it. Building on the code from the previous question, we now see a change to the body statements with a call to free followed by the assignment to v of an allocated integer. Two subsequent calls to free then take place. Click on the tick icon if you believe the code is correct, or the location within the code you suspect is wrong. The code is correct. It is possible to call free, passing it explicitly uninitialized v, as all access type objects are by default initialized to null. Once v has been assigned a target object, it can be passed to free, which will return the target object to storage pool. Free will set any access type object it is given back to null, so the last two sequential calls to free are legal and valid. The key thing to remember is calling free with null has no effect. Our penultimate question again presents the access type targeting integer objects from any storage pool including the stack. We instantiate unchecked deallocation as the procedure free, using both the access type and the target type. Next comes an instance of the access type named v, along with an aliased integer w. In the body, v is assigned access to w, and subsequently v is passed to free. Click on the tick icon if you believe the code is correct, or the location within the code you suspect is wrong. The code is incorrect. It is not legal to deallocate a target object if it is from the stack storage pool, which in this case is true for v, as w is a stack object. In the final question, we declare an access type for integer target objects from any storage pool including the stack. We next see a record declaration, which includes an instance of the access type and an accessible integer. An instance of the record type is declared in the object G, and the procedure P has another instance of the record type locally declared within it called L. The body of P contains two statements that set the access type field target object to the aliased integer field. Click on the tick icon if you believe the code is correct, or the location within the code you suspect is wrong. The code is incorrect. The second body statement breaches the accessibility rules by attempting to use an access type declaration from a lower level in the nesting. The field named v is an access type expecting an accessibility level of at most 0. Thank you for attending this lecture on Ada access types as part of the course on programming in the large using Ada. I hope you have found it a valuable step in learning the Ada programming language, and that you continue on to the other lectures in the course from the Ada University. Thank you.